We have a machine, 0.9 power factor lagging, 60 hertz, 4-pole, Y-connected synchronous generator. There's a synchronous reactance of 2.5, armature resistance of 0.2 ohms at 60 hertz. Friction windage losses are 1 megawatt, and the core losses are 1.5 megawatt. The field circuit has a DC voltage of 120 volts, and the maximum excitation current is 10 amps. The current of the field circuit is adjustable over 0 to 10 amps. The open circuit characteristics of this generator is shown through this IFEA function. IFEA function. This is the function that you've seen that in previous problems. And the reverse one is shown through EEIF. So that's the reverse. So in EEIF, you give the voltage, you get the excitation current. On the other one, IFEA, you give the excitation current, you receive the EA. Okay? And then part A, how much field current is required to make the terminal voltage equal to 13.8 kilovolt when the generator is running at no load. So when the generator is running at no load, we want to know how much field current is required to make the terminal voltage, which is a line voltage, equal to 13.8. This is the OCC, okay, which if you give IF, it gives you basically the EA. Now, through this, you can read, you can go through specific IF to see what basically EA you can receive. But the reverse of that would be when you call the EA IF function. So you give it the terminal voltage under rated conditions, and you read the IF. So that's all it needs to be done. And remember, the machine is at no load conditions, which means that since there is no load on the machine, this voltage would be the same as this voltage since there is no load, right? So you go through that function, you give it basically the 13.8 or 13,800 volts, and you read what the IF value is 3.5. So it gives you field current at no load condition should be this much, 3.5 amps. And keep that in mind, this is basically the line-to-line voltage also, not the line-to-neutral. Line-to-line, to make it more clear. Field current versus open circuit armature voltage, line-to-line again. So that was the first part, which is easy. Second part, what is the phase voltage of this generator at rated conditions? And the rated conditions is coming from this information in here. So the phase voltage is the terminal voltage over SQRT of 3. Rated voltage is 13.8, line to line. Then the phase value of that would be just divided by SQRT of 3. That's because the machine is Y-connected. That's the second part. Then third part, what is the phasor of the internal generated voltage at rated conditions? So the terminal versus basically the internal. So here is what we need to do. So we need to find out the complex power at rated conditions. The complex power comes from the apparent power, SR. What is SR? S under rated conditions is 50 megawatts. And then you have to give the apparent power an angle based on the power factor of the machine to find the complex power. That's exactly that, attaching an angle in MATLAB to a magnitude to find that basically complex number. And then that complex number divided by basically V phase. Complex power, we need to make sure that you divide it over 3. The conjugate of S over V, that becomes the current. Make sure you divide that over 3 because that's a 3-phase machine and we are working on one phase of it, okay? So this gives you that IA under rated conditions, which would be this much with this phasor, this much in the magnitude and this much in the angle. And then EA would be V phase plus the impedance times the current in the generator. So that gives you the internal source phasor of the armature voltage at rated conditions. Now, in part D, we're talking about how much field current is required to make the terminal voltage equal to 13.8 when the generator is running at rated conditions. Remember, because we are working under rated conditions, there is a difference between this voltage and this voltage. Now that we found this voltage is related to the open circuit curve, not this voltage, right? So you have to really look at this voltage. And under rated conditions, this is 13.8, but this voltage is something else, which we found it in here. That's the voltage over there. Now you have to basically apply that through EAIF function. Make sure you basically get the absolute value and multiply that by SQRT of 3, because that OCC is working based on the line voltage, to find the required current in the field. So that gives you that part. So around 10 amps, practically speaking. And then in part E, suppose that this generator is running at the rated conditions and the load is removed without changing the field current. What would the terminal voltage be? Okay. So you were working at rated conditions. Here was a load. Now you're disconnecting that. Now the same voltage that was here will fall on the terminal. As simple as that, right? There's no current in here. So that part E would just multiply that internal voltage by square root of 3 and give you that information. Now part F is how much steady state power and torque must the generator's prime mover be capable of supplying to handle the rated conditions. So remember, you are a generator, right? In a generator, we give power on the mechanical side, we receive energy on the electric side. So therefore, you have to consider all of that input power. What we are calculating is all on the electrical side. Therefore, you need to add up all of those losses associated with the mechanical as well as the core losses and all of that. And also, this is basically representing the copper losses. And this is the output power. So the output power plus all of those losses, that becomes the input power. And the input power is really on the mechanical side. So dividing that input power over the speed in radians per second, that becomes the applied torque. And this is nothing but the speed of the generator under RPM times 2 pi over 60. That makes it in radians per second. So I'm wanting you to construct the capability curve of this generator. The capability curve of the generator must consider 3 basically things. If you go back to the generator, this is the capability curve. It has one first basically circle centered at 0 and equal to 3 times V phi IA. This is the radius. This is associated with the stator current limit. We have another circle. This is the other circle centered at minus 3 V phase squared over XS with a radius of 3 times EA V phi over XS. This is representing the rotor current limit. This is the second. And the third is the prime mover power limit, which is a straight line. Now, your generator would be working under these 3 regions. Now, I've done that for you. The only thing that I want you to know is to find out the right centers and radii of those basically different regions. So this is RS, the radius of the stator current limit, which is 3 times V phase times current. Get the absolute values. And the centers, X and Y of the center, are zeros, right? For the first, this is the first basically circle. For the second circle, the radius is 3 times EA V phi over XS, 3 times E V phi over XS. And basically, your center would be at X equal to 0, but Y should be minus 3 V phi squared over XS. So this is the X 0, and this is the Y. Same value. That is here, minus 3 V phase squared over XS. This is the second circle. The third one is P limit, which we assume it's equal to P in. Consider the power calculated in part F, which was the P in, as the limiting power of the prime mover. So same value that we constructed in F, P in, would be used as the limiting power in the prime mover. Now, this is the function that you need to use, and that function has been provided in here. I don't go into the details of the function, I just explain what it does. So it plots all of those three regions and gets the shaded area between those. Shade curve intersections. This is the radius of the stator limit, center of the stator limit, radius of the rotor limit, center of the rotor limit, and P limitation of the prime mover. You give it, and it gives you just that, basically shaded region. Now I'm going to go over, when I'm finding all of these centers and radius values, just use that in the function. It gives you that basically whole thing. So this is the rotor current limit circle. The blue one is the stator current limit. This dashed line is the prime mover limit. And the allowed region would be the region between all of those. So this gives you that shaded area. So any P or any Q that you're demanding from your generator, if it falls inside this shaded area, it's allowed. You can ask your generator to generate this much P, this much Q, as long as it's inside that area. Okay? So that's actually the next function that I'm going to explain here. So this function is interior, is a function that you give it the P and Q values. The allowed region is coming from this. We already constructed that allowed region. You pass it with the 2 points of P and Q, and it determines whether that's inside that shaded area or not. So I'm telling this function that is 1 megawatt and 6 megawars. 1 megawatt, for example, here 6 megawars would be something around here. Okay, is that allowed or not? Is it inside or not? So just let's pass. It says it's inside. So let's ask another point. If you make it 10 times more, 10 megawatt and 60 megavars, I'm expecting this much. The answer would be 0. No, it's not within that area. Or remember, for the generator, you could go minus, which means that you are receiving reactive power from the grid. Again, but what about this? If you make it just 6 megavars, this point is inside. Okay. All right. So there are two more functions here I want to explain. The first function is get Q limits at P. It means that I'm giving you a P, and I want you to determine the maximum and minimum Qs. So in a certain P, for example, in here, in this, if P is this much, goes here, looks for this point and this point that are on the borders of the shaded area, gives me the maximum and minimum possible Q. And the next function, get P limits at Q. You give it the Q. You give it the Q, for example, at this Q, gives you the minimum and maximum P. The minimum P is always 0, right? The maximum P gives you the maximum P in that region. So these are two other functions that you can utilize. So these are just examples. I put it in this code so that you can work around. So the Q limits for 0 are basically minus 50 megavars and 3.4. This is minus 50. This is 3.4. The important thing is that you understand what are the parameters to these functions. The first function gives you the shaded area. The second function determines whether a point is inside that area or not. The third function, you give it the P, gives you the limits of Q. Fourth function, you give it the Q, gives you the limits of P. In this problem, we have, again, a Y-connected synchronous generator with a synchronous reactance of 2.5, armature resistance of 0.2 ohms. At 60 hertz, the friction windage losses are 1 megawatt, core losses are 1.5 megawatt. Again, the OCC of the generator at synchronous speed and the reverse OCC, I'll make sure I put line to line here. We're assuming that the field current has been adjusted to a value of 5 amps. So we know how much the field current is. Part A, what will the terminal voltage of this generator be? if it is connected to a delta connected load with an impedance of 24 ohm with angle 25 degrees. So we have a Y-connected synchronous generator. Make sure we understand the topology of the system. This is your Y-connected generator. This is your delta connected load. We're connecting these two. In order to have a per phase analysis, convert that delta to Y. That makes our lives easy. So that's what we're going to do in this problem. And then since you have the impedance of your generator, this is the impedance of your generator per phase, you can have these two in series, right? These two in series in phase A. This is the loop for phase A here. For phase B and phase C, similar. So again, once you have the whole impedance, you can just combine these two impedances and have the voltage division. If you're looking at the voltage at the terminal point, this is the voltage division over impedances. This is the first impedance. This is the second impedance. You can have the voltage division concept. I'm going to find the armature voltage per phase. So therefore, I'm going to call the IFEA function, give the IF, get the E, but I need to divide that E by a square root of 3 to make it the phase. So that's what's been done in here. And then ZY, that's the Y equivalent of that delta, which becomes delta over 3, the Z in the delta, divided by 3. So therefore, my VP, this is my VP. My VP becomes EA, this is EA, times the absolute of ZY over ZY plus, this is the impedance of my generator per phase. So this gives me VP, therefore VT, and this is VT. VT is from this point to this point. That's the line-to-line version of it. That becomes a SQRT 3 times bigger than that. So this gives you the VT. Now, part B is asking you to sketch the phasor diagram of the generator. Here we go. This is V phase, RAIA, JXSIA, that becomes your EA. I want you to sketch that, but I know it's hard to do that in MATLAB. Again, I give you a function. That function plots the phasor diagram of the synchronous generator. You give the terminal voltage, you give it the IA, RA, and XS, and it just draws that for you. Part B, this is basically the total. This is a total impedance facing the internal source. This is the angle of the total impedance. Your IA, the magnitude of IA would be EA divided by the absolute value of the total impedance. And its angle would be basically TH. And the phasor would be the magnitude times this angle with negative sign, right? That negative sign is because the impedance goes in the denominator. So this is giving you the IA phasor. And then the plot phasor, you have to give it the V phase, IA, RA, and XS, so that it gives you EA and plots that for you. So this is doing that. So EA would be found. This is V phase, IA, this is RAIA, this is JXSIA, and this becomes EA. All of the legends are shown in here. Now in part C, what is the efficiency of the generator? The efficiency is, this is P out. You get the P out of the terminals. So if this is your generator, you get the power at this point. Therefore, that would be 3 times the real portion of VP times conjugate of IA. And then P in would be P out plus all the losses, which includes also the copper losses. And you get the efficiency of the system easily. Now in part D, it's assuming that another identical delta-connected load is paralleled with the first one. What happens to the phasor diagram? So we just recalculate everything using the new load value. And I've been doing that in here. So this is the first phasor diagram. This is the second phasor diagram. And part E, what is the new terminal voltage after the load has been added? That was calculated in here already. And then finally, what would be the field current to restore the terminal voltage to the original value? So because you added the load, the terminal voltage decreased. You want to bring the terminal voltage back. This is the original problem. You had one load, one generator, and then we added the extra load. This voltage has dropped. Now you put the voltage, you want the voltage to be back to the previous value. So you put the previous voltage back in here, recalculate EA. And through that EA, find IF. That's what's been done in here. So you put the desired VP. This is the desired VP here. And you have the armature current. And you find the basically desired EA. And through that curve, you find the desired IF. So that's what's been done in here. So your new IF should be 9.4664. So your IF used to be at 5 amps. Now, because you added the load, you have to increase your field current to this value so that you can get the same terminal voltage. This is a standalone generator, right? This is not connected to the grid. So therefore, when you add load, your voltage drops, your frequency drops. It's not connected to an infinite bus. This is a single generator operation. So you'll have a 480 volt, 60 hertz, 400 horsepower, 0.8 power factor leading 8-pole delta connected synchronous motor, which has a synchronous reactance of 0.6, negligible armature resistance, ignoring the friction, windage, and core losses. So pretty much we're ignoring all the losses because we're assuming that there is no resistance in armature. Friction and windage, which are mechanical losses, these have been ignored. Also core losses, we assume that there is no core loss. So no loss in the system. We assume that EA is directly proportional to the field current. So we know that EA and field current are related through the OCC curve. Here, we're assuming that the relationship is linear, which means we don't go into saturation. EA would be 480 when IF is 4. And this is a linear relationship. So this means that if you make IF equal to 2 amps, EA would be half also. What is the speed of this motor? Well, the speed of the synchronous motor doesn't have anything to do with any operational conditions. We always find it equal to be equal to 120 F over P. So this is the motor's basically speed, which is 900 RPM. If the motor is initially supplying 400 horsepower at 0.8 power factor lagging, what are the magnitudes and angles of EA and IA? So this is simple calculation. You have the complex power. This is a show of lagging power factor. You find IA. Remember, since you're doing the per phase analysis, divide the complex power over to find IA. And then you have IA, you can find EA. Remember, the direction of the current in the motor is reversed. So if this was generator, you would put a plus here, but for the motor, you put a minus. This becomes your EA. Part C, how much torque is this motor producing? The torque comes from P divided by speed, right? And since P in and P out are the same, since there is no loss, this tau would be both the applied torque on the mechanical side and also the electromagnetic torque. These are the same values. Delta would be the angle of EA, which would become the torque angle. That's a torque angle. How near is this value to the maximum possible? So the maximum power, maximum torque, would be 3 times V on the two sides divided by XS times NM. And then sine of delta is 90 degrees. So again, let's go to motors. The maximum torque. Here, this is the torque. This is the maximum torque when sine of delta is 1. This is coming from there. So this is the tau that we are having. This is the maximum tau that we could have. And you see how bigger this is versus them. Then in part D, it's asking if EA is increased by 20%. And remember, the relationship between EA and IA was linear. What would be the new magnitude of the armature current? Remember, we are increasing EA, but we haven't changed torque or power, okay? So the power is the same, torque is the same, just EA has changed. We want to see what change will happen in the armature current and what would be the motor's new power factor. If you're assuming that your motor is lossless, which is the case that we have, then P would be 3 times. If you're assuming that the terminal voltage and XS are constants, therefore EA1 sine of delta in the first condition would be EA2 times sine of delta in the second condition. So from here, you have the first condition. You know you're going to increase your EA2. Therefore, you will find your new delta angle. Okay? So that's what we did in here, to find the new delta angle. Once you find the new delta angle, then you can find out the new EA, and you can find the new IA. So this is going to be the new armature current. The last part of the problem is that it wants you to calculate and plot the motor's V curve. What is motor's V curve? That IA versus EA. What we did in here was to increase basically EA by 20%. So we're going to repeat this when we change EA between 75% up to 170%. 75% up to 170% of the original value. So this is kind of an extension to part D and plotting the values with respect to each other. So instead of doing that by 120% only, we're going to change it from 75% up to 170% and recalculate everything and then plot EA versus IA. So this is what's been done to give you IA versus EA.